Crown Seminar. Our first speaker is Yongcun Song, who is currently a postdoc in the Department of Mathematics, University of Erlangen-Nürnberg, Germany. Before that, he received his PhD from Department of Mathematics, the University of Hong Kong in 2021. His main research interests are numerical analysis and scientific computing, including numerical optimization, operating splitting algorithms, machine learning, and opening control problems. Today, he'll be talking to us about pins for non-smooth PDE-constrained optimization problems. Welcome. So you may want to start the presentation.
Okay, thank you. Okay, thank you for the introduction, and thank you very much for the invitation. And I'm very happy here to share some of my recent work. And today I will talk about fit-formed neural networks for non-smooth PDE-constrained optimization problems. Okay, first we will talk about some backgrounds and the motivations about PDE-constrained optimization and physics-informed neural networks. And then we will focus on two typical examples. It's called parabolic sparse optimal control problems and elliptic interface optimal control problems to illustrate our main ideas in the design of physics-informed neural networks for solving non-smooth PDE-constrained optimization problems. And finally, there are some conclusions and perspectives. Okay, first, partial differential equations model various physical phenomena such as diffusion, heat flow, fluid flow, and so on. And for some applications, we need not only to model certain physical process, but also control or optimize the considered process to optimally meet certain objectives. So we need to minimize a given objective functional and subject to a PDE or a system of coupled of PDEs, and usually with some additional constraints. So PDE-constrained optimization problems arise. And here is an example of control the heat distribution of a metal bar. And mathematically, a PDE-constrained optimization problem can be represented as this model. And here, U and Y are Banach spaces or some other proper function spaces. And UAD and YAD are closed convex sets. And G is objective functional to be minimized. And E represents a PDE or a system of coupled PDEs. That is, we use this PDE to describe the physical processes that we are interested in. And the data variable Y describes the state, for example, the temperature distribution of the considered system modeled by this equation. Okay, and the control variable U, or maybe called the design variable, okay, maybe some other names, is a parameter, for example, the thought term in the equation that shall be adapted in an optimal way. And the control constraint U belongs to UAD, and this data constraint Y belongs to YAD describes some physical restrictions and realistic requirements. Because in practice we cannot apply the control in an upper way. There are always some restrictions. And we would like to find a variable U and Y such that they satisfy the equation EUY equals to 0 and satisfy the additional constraints U belongs to UAD and Y belongs to YAD. Well, they minimize the objective functional J. Okay, this is the model of a PDE-constrained optimization. And here we consider some non-smooth cases, and we consider two types of non-smoothness. Okay, the first case is the objective functional is non-smooth. Okay, here we write the objective functional in this form. And the functional G consists of a data fidelity term and a possible smooth regularization. And generally we assume this G is smooth. And R is a non-smooth functional, and it is used to capture some prior information on U. such as sparsity, discontinuity, or the boundedness. Okay, if we would like to promote the sparsity, we can employ RU as L1 regularization, and the discontinuity can be achieved by TV regularization, and the lower and all upper bounds can be achieved by if RU is an indicator functional of an admissible site. Okay. And here we focus on this specified example to make our statements more clear. And here we consider a parabolic sparse optimal control problem. Here we consider such an objective functional. Okay, the first two terms means, the first one is the data fidelity term. That means we would like the state variable y is close to yd, okay, as much as possible. And the second term is smooth regularization. And the last two terms, marked by blue, are the non-smooth terms. Okay, the L1 regularization is used to promote the sparsity of the control variable u. Here, the sparsity means the support site of the control variable is only a subset of the domain. That means, in some parts of the domain, the control variable is 0. And then the IUADU is the indicator function of a site UAD. Okay, and the state equation is a parabolic equation. And the admissible site UAD is defined in this way. So if we add this IUADU, we impose some lower and upper bounds on the control variable. So with this non-smooth regularization, we can promote the control variable is sparse and is bounded.
Can I ask something? So the non-smoothness comes only from the L1 term.
Oh yeah. Of course, in fact it is.
So, but J, like in the top, J is a smooth. Otherwise, J of YU, for example, is that part is smooth, right? On the top equation. The first term on the right-hand side is a, and then R of U, then because the term that has the L1 is a regularization. That's what you mean, right?
Oh yeah.
So the only non-smoothness comes from the penalization on the L1 norm, or is the functional also not non-smooth? I mean the objective. I'm trying to see where. I guess, yes, it is all the terms that you have, so that's it. Yeah.
Oh, yeah. Okay, this is the first case. And
sorry for this. So the solution itself is the solution of the PDE. Is that smooth or non-smooth, or it doesn't matter?
Oh, the solution of the PDE is smooth because it's just a standard
parabolic. Because it's parabolic. Yeah.
Oh, yeah.
Okay.
Yeah, thank you. And the second type of non-smoothness is we consider some non-smooth PDE. That means, the solution of the PDE is non-smooth.
Okay.
Yeah. And here we focus on some interface problems. And interface problems is a piecewise defined PDEs in different regions coupled together with interface conditions. For example, jumps in solution and flux across the interface. Hence, the solutions is non-smooth or even discontinuous. Okay. And then this is an illustration of the geometry of an interface problem. That is, this is the whole domain omega, and this is a interface, and it divides the whole domain into two subdomains, omega minus and omega plus. And the PDEs and the interface problem, is a piecewise defined PDE in omega minus and omega plus, and the solution of this PDE is non-smooth or discontinuous across this interface. Okay, and here is an example. Okay, and here we focus on an elliptic interface optimal control problems, and the objective functional is smooth. Okay, is a very standard L2 norm, and here the state equation is an elliptic interface problem. Okay, here beta is a piecewise constant, And it is beta minus in omega minus and beta equals to beta plus in omega plus, okay? And the jump discontinuity across gamma is defined in this way, and that is, on both sides, on different sides of the interface, the function value is different, and the jump is defined in this way. And this is the jump of the normal of derivatives. Okay, and we note here, if G0 and G1 are zeros, then the solution is still non-smooth. Okay, because we look at the last line, okay, the definition of the jump of normal derivatives. Okay, if G1 is 0, the normal gradient, the normal derivative, on different sides of the, okay, sorry, there's a typo, there's omega minus, okay. The second term is omega minus, in different sides of the interface is also different, so the solution is non-smooth. Okay, so in the following discussions, we will focus on these two types of non-smooth PDE-constrained optimization, and then we would like to design some pins algorithms for solving these two kinds of problems. Of course, for solving non-smooth PDE-constrained optimization, there are some numerical methods that have been developed in the literature, and all these methods are featured by optimization algorithms plus numerical discretization. And optimization algorithms include semi-smooth Newton methods, primordial active set methods, alternating direction methods of multipliers, primordial methods, etc. Okay, these methods can handle the non-smoothness of the objective functional. Okay, and then the numerical discretization, of course, is some finite difference methods or some finite element methods. And the implementation of these methods are usually based on the so-called adjoint methodology. And that means if one we would like to derive the first order optimality system of PDE-constrained optimization, we always consider the adjoint system. Okay, so two PDEs that are the state equation and its adjoint system, or a set point problem. That means the first order optimality system are usually required to be solved repeatedly, because we always employ some iterative scheme, some iterative optimization algorithms, and at each iteration we need to solve such systems. So we need to solve these two PDEs or a set point problem repeatedly. And after some proper numerical discretization, the resulting systems are large scale and ill conditioned. So the computational cost for solving the PDEs or the set point problem repeatedly could be extremely high in practice, and especially for some high dimensional PDEs. And these methods are strongly problem dependent. For example, different types of PDEs require different numerical discretization schemes. For example, for the models we considered here, for the discretization, for the spatial discretization of the parabolic equation, we can employ the standard piecewise linear finite element method. But this finite element method does not apply to the interface problem, because it cannot enforce the jumps and other interface conditions. So we need to develop some other numerical discretization schemes for the interface problem, like the immersed finite element methods. Okay, so these traditional numerical methods have these numerical issues, and to avoid this, we consider some deep learning methods. Okay, and recently deep learning has emerged as a new powerful tool for solving PDEs, and there are some representative deep learning methods. Include the deep race method and deep galaxy method, and physics-informed neural networks, and the random feature method. Okay, there's a typo, sorry. And this kind of methods approximate the unknown functions in a PDE, and then train the neural network after training the neural network, we can get an approximate solution of the PDE. And of course, there is another type of deep learning methods. It's called operator learning methods. And this operator learning methods approximate the solution operator of a PDE. And here we focus on the physics-informed neural networks because it seems that physics-informed neural networks is the most popular one, because it is very easy to implement and has great power in many applications. And PINs can be viewed as a scientific machine learning technique used to solve different differential equations. And the main idea of PINs is to approximate the PDE solution by a neural network, and then train the neural network by minimizing a loss function consisting of the residuals of the PDE and the other boundary or initial conditions at selected points in the domain. And given an input point, and PINs can produce an approximate solution in that point of a PDE after training. Okay, this is the main ideas of PINs for solving PDEs. Okay. It's just a standard procedure of the PINs. Okay, we first approximate the solutions by a neural network, and then we specify some residual points in the domain and on the boundary. And then we specify a loss function by summing the residuals of the PDE and the boundary condition. Okay, and then we train the neural network. And PINs have a lot of nice properties. For example, little or even no labeled data is required, and it is easy to implement, and it is mesh-free and flexible to different problem settings. And there are some review papers that discuss some applications and some other aspects of PINs. And of course, for the PDE-constrained optimization, there are some papers to study the PINs for smooth PDE-constrained optimization. And the idea is also very simple. Just combine the residuals of the PDE and the objective functional. Okay, but here we know that in a PDE-constrained optimization, U and Y are unknowns. So we use two different neural networks to approximate U and Y, and then to train the total loss, to minimize the total loss to train these two neural networks. Okay, the ideas is very similar to the PINs for PDEs. And another idea of PINs for solving PDE-constrained optimization is we first derive the first order optimality system of a PDE-constrained optimization, and then apply PINs to solve this first order optimality system. Okay, we will present this idea in the following discussion. And although the PINs have been successfully applied to smooth PDE-constrained optimization, but for the non-smooth cases, there are some challenges. For the parabolic sparse optimal control problem, and the non-smooth term, okay, appears in the loss function. Okay, if we approximate the control variable U by such a neural network, and then because it is non-smoothness, commonly used neural network training technology, for example, the backpropagation and the stochastic gradient methods cannot be applied directly. And for the elliptic interface optimal control problem, the discontinuity or non-smoothness of Y cannot be well captured by the neural network, because typically we use smooth activation functions. Okay, for example, the sigmoid function, or at least continuous, or in other words, it is almost everywhere smooth. For example, the ReLU function. Okay, so the resulting neural network can approximate continuous function very well, but for this discontinuous function, the approximation is not very good. So in the following discussions, we will talk about how to address these two issues. Okay, so first is the ADMM PINs for the parabolic sparse optimal control problems. Okay, we first recall the parabolic optimal control problem we investigated. Okay, we can see if there's no the last two non-smooth terms, we can apply pins to solve the resulting smooth optimal control problems directly, right? There's no any problem. But here, the Nonsmooth terms is coupled in the problem. So if we separately, then the rest part of the problem can be handled by pins. Okay, and to achieve this goal, we consider operator splitting. Okay, that means the PDE constraint and the Nonsmooth regularization are treated individually, and then we split the original problem into two sub problems, and it admit closed form solution. All can be solved directly by pins. Okay. And for this purpose, we consider the alternating direction method of multipliers, okay, and ADMM for short. It is a representative operator splitting method introduced by Golotsky and Marocco in 1975 for solving nonlinear elliptic problems. And to apply the ADMM, we first introduce an auxiliary function z such that u equals to z. Then we can write the parabolic sparse optimal control problem into this form. Okay, this is an optimization problem with a separable structure. Okay, here yu is the solution of the parabolic state equation corresponding to u. Okay, in this way, the smooth part and the non-smooth part can be treated separately, and they are connected by this simple linear constraint. Okay, and then we introduce the augmented Lagrangian functional of this optimization problem, and the augmented Lagrangian functional is in this form. And here, lambda is a Lagrange multiplier, and beta is a penalty parameter. Then the ADMM iterative scheme is in this form. Okay, first, given zk and lambda k, we update zk plus 1 because it is only a problem in terms of u. Okay, and then with this computed uk plus 1, we can solve the subproblem of z. And finally, we update the Lagrange multipliers. Okay, so actually, the ADMM is a splitting version of the classical augmented Lagrangian method. And that means if we solve the subproblem of u and z together, then we get the augmented Lagrangian method. But here we split this subproblem in a Gauss-Seidel manner. Then we first look at the z subproblem. Okay, by the definition of the augmented Lagrangian functional, the z subproblem is just a very easy optimization corresponding to these two of this non-smooth regularization. Okay, and it has a closed form solution. Okay, that is the solution zk plus 1 can be computed by this form. Okay, here P is a projection onto the site UAD. Okay, because UAD is very simple, so the projection can be computed can be easily computed. And here S is the shrinkage operator. Okay, it is a very well-known operator in dealing with L1 regularization. Okay, it is defined in this form. So for the update of zk plus 1, we can easily compute by this formulation. And then for the U subproblem, it is clear a standard smooth parabolic optimal control problem, because yu is a solution from the parabolic state equation, but with a slightly modified objective functional. But we can apply pins to solve it directly. Right? And here we first derive the first order optimality system of this U subproblem, and it is in this form. And the first one and the last one is the adjoint equation, and P is a adjoint variable. Okay. And next, we consider applying pins to solve this first order optimality system. Okay, first, if we apply pins directly, we need to approximate U, Y, and P by 3 different neural networks. Okay, and then we need to train 3 neural networks. And to reduce the training difficulty, we use the first equation of the first order optimality system to write U in terms of P. And then we substitute this equation into the second one. We can eliminate U and obtain a reduced optimality system in terms of only Y and P. And then we construct 2 neural networks of Y hat and P hat to approximate the state variable Y and the adjoint variable P. Okay. And then we can apply pins directly. Okay, this is the loss function. Okay, only consists of P and Y. After training these 2 neural networks, we can then update UK plus 1 by the relationship between U and P. Okay. And this is the resulting ADMM pins algorithm. Okay, we first initialize the variable Z and lambda, and then we can update ZK plus 1 and initialize the neural networks, and then we can update UK plus 1 by the above pins method, and then update ZK plus 1 and then lambda K plus 1. Okay, the updates of ZK, Z and lambda are very easy and cheap. And finally, we can output the approximate solution Y hat and U hat. Okay, and in this way, we can handle the non-smoothness and to guarantee the sparsity of the control variable. And next, there are some numerical results. There's problem settings, and this the details of the neural networks and training. And these are some numerical results. Okay, the first row is the exact control at a different time, and the second row is computed control at a different time. Okay, we can see the sparsity, the spatial sparsity of the control. Okay, that means, you know, in some parts of the domain, the control variable is 0. And the exact and computed controls are almost the same, and there is no difference visually. Right? And for this example, in addition to the spatial sparsity, we can show that the temporal sparsity. That means if T is large enough, the control variable U is 0. Okay, and by the problem settings, we can show that if T is larger than 0.8211, then the control variable is U. You know, as shown in this figure. Okay. And the total relative error on the whole temporal spatial domain is about order of 10 power minus 2. Okay, it is an acceptable accuracy. So, so this result shows that, you know, our proposed ADMM pins can efficiently handle the non-smoothness of the problem. And as we said, we focus on the parabolic sparse optimal control problems to make our statements more clear. And for more applications of the ADMM pins can be found in the paper. Okay, other applications include the optimal control of Burger's equation and some other inverse problems. And next, we talk about the hard constraint pins for elliptic interface optimal control problems. Okay, and we first recall the elliptic interface optimal control problem. Okay, and the key point is the non-smoothness or discontinuity across the interface. Okay, and we first derive the first order optimality system. Okay, the first. And here again, P is the joint variable. And here the interface condition of P is homogeneous. But as I saw, even homogeneous interface conditions, the joint variable P is still non-smooth. because data is a piecewise defined the constant. Okay. And for this kind of interface problem, the key point is to deal with the smooth or the discontinuity of the solution to the equation, right? And here we consider some smooth extension. Here the function y is only piecewise smooth. Okay, it is smooth in the domain omega minus and the subdomain omega plus, but a jump across the interface. So it is only piecewise smooth, but it can be extended to a d+1 dimensional function y tilde x z. And here the additional input z is augmented coordinate variable that labels omega plus and omega minus. And that means, okay, if x belongs plus, y tilde 1 equals to yx, and yx equals to y tilde x minus 1 if x belongs to omega minus. Okay, and this idea, this smooth extension idea, can be seen from this example. Okay, if we look at these two red lines, okay, it is a step function in one-dimensional space. Okay, and it is discontinuous at x equals to 1, right? But we can make some smooth extension. For example, the shadow part, okay, we connect to the endpoints, and then the shadow part is clearly a smooth surface in two-dimensional space, right? So the shadow part is just our y tilde xz. It is smooth. Okay. And similarly, one can extend P to a d+1 dimensional smooth function P tilde. Okay. Then we substitute y tilde and P tilde into the first order optimality system. We obtain that y tilde and P tilde satisfy this system. Okay. And then because y tilde and P tilde are smooth functions, we can use some neural networks with smooth activation functions to approximate them, and then pins can be applied. And since y tilde and P tilde are continuous in this augmented space, it follows from the universal approximation theorem. One can approximate them by two shadow neural networks, y hat and p hat. Okay. And such neural networks are referred to as the discontinuity capturing shadow neural networks. Okay. And then pins can be applied. And this is the loss function in pins. Okay. This loss function, okay, is formulated by combining all the residuals in the first order optimality systems together. Okay. The first, okay, the blue parts are the boundary conditions of y and p, and the red parts are the interface condition of y and p. So there are 8 weights should be selected. Okay. Then there are some numerical results, and we can see the maximum value of the error is about order of 10⁻⁻3. So it is an acceptable accuracy, right, compared with the exact control. Okay, but in the above pins, the boundary and the interface conditions are penalized in the loss function with constant penalty parameters. So they are treated as soft constraints and cannot be satisfied rigorously. Okay, so the ball pins is a soft constraint pins. And the boundary and the interface conditions as well as the PDE are treated together during the training process, and its effectiveness strongly depends on the choices of the weights in the loss function. And to my knowledge, there is still no established rule for choosing these weights, and manually determining these weights is challenging and time demanding. And also, The above numerical results show that the numerical errors mainly accumulate at the boundary and the interfaces. Okay, let's go back to this. Okay, we can see that the numerical errors accumulated at the boundary and the interface for the both control U and the state Y. Okay, so to address these issues, we consider imposing the boundary and the interface conditions as hard constraints so that they can be satisfied exactly in the neural network architecture and can be treated separately from the PDE in the training of the neural networks. Okay. And the strategies to impose the hard constraints is to develop a neural network architecture by generalizing the DCSNN to approximate Y and P. And in particular, we would like to modify the output of the neural network to impose the boundary condition and to modify the input of the neural network to impose the interface condition. And here we construct an auxiliary function for the interface as an additional feature input of the neural network. Okay. Okay. Next, we introduce our new neural network architectures. Okay. We would like to impose these two conditions, okay, the boundary condition and the interface condition. And then we approximate Y by this neural network. Okay, here G X satisfies, at the boundary, it is just the boundary condition, and it satisfies the interface condition, and it is piecewise, in C2, and the function H satisfies, it is C2, and it is 0 if and only if it is if X belongs to the boundary. And here, the function phi is an auxiliary function for the interface. Okay, it satisfies the following conditions, and this function phi is used to guarantee the interface condition. Okay, and here we know that the last requirement, that is the jump of the normal derivative is non-zero because we need to capture the non-smoothness caused by the jump of the normal derivatives. Okay, and here NY is a neural network with smooth activation functions. And then we verify the boundaries and the interface condition. And first, because the construction of HX and Y, we know this function is a continuous function of X over the whole domain. And then we check the interface condition. Okay, this because the second part is smooth, and the G satisfy the interface condition. So Y height satisfy the interface condition. Okay. And the boundary can also satisfied. Okay. And next, with this neural network right, we can compute the jump of the normal derivatives in this form. That means the interface gradient condition cannot be exactly satisfied by this neural network, and should be penalized in the loss function of pins. Okay. And next, we discuss how to choose these auxiliary functions. Okay. And for the boundary conditions, imposing boundary condition constraints is not a new topic. There's some references to discuss these questions. Okay. Here we list some references. So that means if the functions G0, H0, and the interface and the boundary admit analytic forms, it is usually easy to construct G and H. Okay, and for the choice of phi is a little bit delicate. Okay, if gamma, the interface gamma is the zero level set of a function in CK omega, maybe we call this function Vx, okay? Gamma is the zero level set of Vx belongs to CK omega. Then phi can be easily constructed. For example, if it is a circle-shaped interface, that is a circle. And then we can define the auxiliary function phi in this form. That is, in the subdomain omega minus, we just consider the function Vx. It is smooth, okay, in CK omega. And then on the interface and in the domain omega plus and the boundary, we just take 0. And in this way, we can construct phi x, and it satisfies all the requirements. Okay, it is continuous on all domain, and in each subdomain, phi x belongs to the C2 omega. Okay, and another example is box-shaped interface. Okay, the idea is the same. Okay, just take the function omega minus, and then we take zeros. But if the interface is not the 0 level set of a smooth enough function, and we have shown that if the domain, the subdomains, and the interface set by the following assumptions, then we can construct an auxiliary function phi x analytically. Okay, maybe this assumption look a bit complicated, but the main idea is, the gamma is the zero level set of some functions. These functions are not continuous on the whole domain, but only smooth on a neighborhood, open neighborhood of the interface gamma. Okay, if there exists this kind of functions, smooth functions, we can construct the function phi in this way. Okay, then we can prove that it is well defined and satisfy the requirements that we imposed on the function phi. Okay, and this is an example of the theorem to illustrate the theorem. Okay, here we consider omega is a two-dimensional bounded domain and contains a star-shaped interface. Okay, it's illustrated in this figure. Okay, and it is the 0 level set of this function. Okay, in polar coordinates. Here the is not differentiable on omega because the polar angle is not differentiable at the origin. And in this case, by the results of the above theorem, we can define the auxiliary function phi in this form. Okay, and then we can check this function satisfy all the requirements of the auxiliary function and works very well in numerical experiments. Okay, and there are some remarks on the choices of auxiliary functions. Okay, if the functions g, h, and phi are difficult to construct analytically, we can construct them by training some neural networks. Okay, for example, we can train a DCSNN G hat and a neural network H hat with smooth activation functions by minimizing the following loss functions. Okay, to approximate G and H. Okay, because the simple structures of these loss functions. Okay, and we only consider some points, maybe on the boundary or interface. Okay, this kind of loss functions are relatively easier to minimize, and we can get a highly accurate approximation of this auxiliary functions. Okay, and then with above discussions, we approximate y by the neural networks, a neural net y hat. Okay, and then for the adjoint variable p, okay, the boundary and the interface conditions are homogeneous, so we can take g, the function g is 0. Okay, and then we approximate it by p hat defined in this way. And here, hx and phi x are the same as the ones in y hat. And with these two neural networks, y hat and p hat, we can apply the pins to solve the elliptic interface optimal control problem by minimizing the following loss function. Okay, compared with the soft constraint pins, okay, there are 8 terms, and we need to to select 8 weights. And here we only need to handle 4 terms, and it is much easier to train. Okay, this is the results of the hard constrained pins. Okay, we can see that the maximum value of the error is about order of 10 power minus 4. Okay, it is 10 times more accurate than smaller than the soft constrained pins. Okay, and there are some other numerical comparisons. Okay, for the absolute value and absolute error and relative error for the soft constrained pins and hard constrained pins are listed here, and we can observe that the hard constrained pins improves the numerical accuracy by more than 20 times. And for the numerical errors, we can see that the soft constrained pins, the numerical errors are accumulated at the boundary and the interface, right? But for the hard constraint pins, because we impose these 2 conditions at the hard constraints, so this phenomena disappears. And again, to illustrate our main ideas clearly, we only focus on an elliptic interface problem. And for more numerical results on the hard constraint pins for other interface optimal control problems can be found in this paper. Okay, finally, there are some conclusions and perspectives. Okay, it is challenging to apply pins directly to Nonsmooth PD constraint optimization problems. And combine pins with classical operator splitting optimization techniques, for example, the ADMM, leads to implementable and efficient algorithms for PDE constraint optimization problems with non-smooth objective functional. And leveraged by the discontinuity capturing neural networks, pins can be applied to solve interface optimal control problems. Okay. And then by imposing the boundary and interface conditions as hard constraints, we further improve the numerical accuracy and simplify the training procedure. And in the future, we will study the theoretical analysis, because here we only consider the algorithm design and the design of the neural networks and to do some numerical simulations. And there is still no theoretical guarantees for these 2 algorithms. And we are now working on these theoretical issues, such as the convergence analysis and the error estimate. And that's all. Thank you. Thank you for your attention.
Yeah, thank you for your presentation.
Thank you.
Is there any question for our speaker? Comment? Suggestion?
Yes, some of this work, we had a speaker who published a book, The Theory of Functional Connections, Daniele Mortari, who actually decomposes the constraint problem to unconstrained problem, including these continuities.
Oh, okay.
So he's from Texas A&M. He has a whole book on that, actually, and he applied to not controls problem, but basically the same idea: hard constraints versus soft constraints, especially. Can you do that for all solutions, including discontinuous solutions? So he had. So you may want to look at that. His name is Mortari, Daniele Mortari.
Okay, thank you for the suggestion, Mortari.
And I also have another question. You didn't compare the ADMM pins with other methods, like the adjoint methods. Have you done it and you didn't show us, or the reviewers didn't ask for it?
We have done it, privately, because this example we have solved it before using some finite element methods,
Right,
and then find some other optimization problems, algorithms. If we only focus on the computer time, the pins methods is less efficient than the adjoint methods. Yeah, but the one of the advantages of pins is it can handle some complicated domains, and and it can be, easily adapted to other problems.
Okay.
Yeah.
Hello, this is Lulu. So then how about accuracy? So your pins can show similar accuracy, I mean, the final objective value at the joint method, or it's different?
You mean the objective function value, right?
Yes, because eventually we try to have either the smaller or larger objective value, right? We have
combined with the joint methods, right?
yes.
Yeah. It depends on the mesh size used in the finite element methods. In our cases, if we use, the mesh size is about 100, 1 over 100, the objective functional is comparable to the pins. But if we decrease the mesh size, then the function value, the objective functional value can decrease. But for the pins, it seems that it keeps stable even if we add some training points.
Okay, I see.
Hi, Yongcun. This is Chen Ye from Brown. I have a question about the augmenting Lagrangian method in the first part.
Okay.
So,
okay, it's here.
Yes. I think there is a parabolic equation control in the original problem, but why there is no this term in the ADMM method? Okay,
actually there has. Okay, for the use of a problem here, YU, okay, it represents the parabolic solution. So if we would like to compute YU, we need to solve the parabolic equation. Okay, we just use a different notation. Okay, if we write here y and u satisfy the parabolic equation, so there's still a parabolic equation.
Okay, got it. Thank you.
Are there any other questions for our speaker? So yeah, we still have time. We're waiting for our second speaker to join. So if you have questions or any comments, discussions, there's time.
I have one more.
Go ahead. Oh, I'm sorry. I think Matthias, you just put something in the chat, right? So you may want to.
This was just Mortari.
Yeah.
So maybe I have two things. So first, to comment these elliptic problems with these step boundary conditions at the interface. This also appears in domain decomposition problems. So if you have a lot of elliptic problems and you try to fix them together, so maybe this is also an interesting direction, domain decomposition.
Yeah, there is some work, to combine the domain decomposition and pins to solve this kind of interface problem. And but there's one problem, that is, if we imply the domain decomposition, we need to use different neural networks on different domains. For example, for the example we considered here, to approximate the state variable y, we need one neural network to approximate y in the domain omega minus, and another neural network to approximate y in the domain omega plus. And that means we need train two different neural networks. And if we employ this smooth extension, we only need to train one neural network to approximate y.
Yeah, it doesn't sound very efficient. My second point is more mathematically. So you started with a problem formulation that was based on Banach spaces, but later, for example, here then you used the inner product of the L2 space. So are you working with Banach spaces or Hilbert spaces?
Okay, this means, actually, I'm sorry for this, unclear statements. And here we consider some Banach space, but this kind of Banach space, here we assume that the L2 product can be defined. For example, here we consider, for example, the TV regularization. It is in BV space, but in 1- and 2-dimensional space, we consider that is the BV intersect L2 space. And when the space dimension is 1 or 2, this space is a Banach space, but it is equals to the L2 space.
Okay, that clarifies. Thanks.
Yeah, I will try to clarify in the slides.
Okay.
Yeah, it's indeed a Banach space because we use another norm, but it is a subset or equivalent to the L2 space.
Thanks.
Is there any other question? Comment? All right. Thank you, Yongcun, for joining us, for presenting your work in our current seminar. Yeah, we really appreciate it. So now we move to our second talk. Of course, you're welcome to stay. Prashant, are you here? Oh, I see.
Hi,
Hi, thanks for joining earlier. Okay, so our second speaker is Prashant Jha, who is currently a research associate at the Oden Institute for Computational Engineering and Sciences, the University of Texas at Austin. He joined UT Austin as a Peter O. Dunlap postdoctoral fellow in August 2019. Before that, he worked as a postdoctoral scholar at the Department of Mathematics at Louisiana State University. In August 2016, Prashant obtained his PhD in Civil and Environmental Engineering from Carnegie Mellon University. He is interested in developing and applying mathematical models and computational methods to engineer problems. The current focus includes the mechanics of a function of soft and granular materials and the computational design of such materials. Welcome. You may want to share your screen and start the presentation. Okay.
Can you see the screen?
Yes.
Okay, so let me first of all thank Professor Karniadakis for this opportunity. I really appreciate it. So today I would like to present this talk more in an informal way. The reason is that I just got an offer for a position in UK, and I'm just going through the negotiation for that offer. So I'm kind of occupied with that also. But I did prepare this talk fully. So hopefully I'll cover all the topics I want to cover. So let me start the presentation. So the topic of this work is basically looking at neural operators as a means to approximate partial differential equation based models. And the question we want to ask is there a way to enhance their accuracy and reliability by some additional problems to be solved? And the answer is yes. So basically this work is about the story of how we got to that problem. It's nothing fancy, but how we got to this approach of enhancing the accuracy, and show you some interesting examples where we do see like almost 2 orders of increased accuracy with this approach. Okay, and this is really a joint work with my colleagues here at Oden Institute. So my manager, Dr. Oden, and also postdoc here, Liang Hakao, and then another research associate here, Thomas O'Leary Roseberry, and also Professor Omar Ghatas. Okay. So here is a quick outline. So we'll first look at what is the overall goal of this talk and what kind of problems we are interested in. So I'll briefly talk about that, and then I'll talk about the motivation of this work, which really goes to the modeling error, our work on modeling error that started with goal-oriented a posteriori error estimation. So I'll briefly talk about that because that really sets the foundation of the corrector approach. And then we'll look at approach of goal-oriented a posteriori error estimation in estimation of parameters in half-relative model. And then from there, we'll talk about how to use that approach in enhancing accuracy of neural operators. And then I'll conclude. So first of all, let me define neural operators in a very simple manner. So neural operators are approximations of a mapping between function spaces based on neural networks. So consider a partial differential equation in a weak form. So you have residual R as a function of model parameter theta, a forward solution U, and then test function V equals to 0. And this gives you what is called solution operator. So given model parameter theta, f of theta gives you the solution of this weak form. Okay. Now neural networks are basically approximation of this map f. So given theta, it gives you a solution, and we wish to develop a approximation of this map through neural networks. So I will call it FNN of theta. And there are some challenges with neural. I'm sure people here are experts in this area, so they are aware of these challenges. One is that their accuracy is unpredictable in the sense that we train to minimize the error in neural network, but we don't know a priori that for given samples, input sample, what would be the accuracy. It could be high, it could be low. If the input is within the training input subspace, then accuracy could be controlled and it will be within some error. But if it's a little bit far away from the input subspace, it could lead to very large error. The other limitation, which is also a limitation with any surrogate model that we should develop, and that is generating appropriate training data. So imagine solving a topology optimization problem, and a priori you don't know what the optimal model parameter will be as a solution of that topology optimization problem. And therefore, a priori you cannot generate training data that is representative of those optimal solution. So if you don't know right parameter space where you are going to solve your model problem over and over again, and if you don't have training data that is representative of those regions, then you can train neural network to achieve certain accuracy, but when you actually use input from those regions, it could lead to large error. So very typical of any surrogate approximation actually. And this is related to, okay, so having said that, the question that I want to ask in this talk is there a way to enhance the accuracy of neural operators beyond what is possible through hyperparameters and architecture tuning? So there are multiple architectures for neural operators. You have many hyperparameters, So beyond what you can achieve by changing architecture or tuning hyperparameter, can you increase the accuracy further? Right? And this really is related to modeling error. So here is a model, here is the approximation, and we are basically looking at modeling error and some kind of way to control that modeling errors or find a mechanism to enhance the accuracy of modeling error, right? So this brings me to the second topic, which is a topic of modeling error, and from there we are going to look at the approach to enhance the accuracy. So let me start with the abstract problem. So we are looking at this abstract problem where we are seeking a solution of this equation 1, where A is an operator, it's a differential operator. It depends on model parameter theta, U is a forward solution, and there is some given forcing function F. We can then convert this problem, which is strong form, into a weak form. So you have some semilinear form B, which depends on the model parameter theta. It can be nonlinear on U, and then there is test function B, and there is linear form L. Now the goal of this problem is ultimately to compute quantity of interest, QOI, right? So there is a functional Q, and given a solution of this problem, we want to evaluate that functional Q, okay? Now we'll assume that this problem 1 is intractable or it's expensive to solve because possibly A is nonlinear, depends nonlinearly in theta and also in U. And therefore we are prescribed with some kind of a lower fidelity approximation of that problem. So the new problem is basically given U0. So new problem is finding a solution U0 of this lower fidelity problem. So where A0 is a surrogate operator. It has its own parameters, theta 0, and U0 is solution of that. And we keep the forcing functions F same. This leads to another variational formulation, and we can compute as a solution of this problem, we can compute QI as an approximation of a Q of U of high fidelity solution. Okay, so the goal now is how to estimate this error. So this error, which is an error in quantity of interest, is called the goal-oriented error because QOI is the goal of the problem, and therefore this error is called goal-oriented error. And the problem is it possible? The question that we ask is it possible to estimate this error without solving the full high fidelity problem? Of course, if you can solve the problem, you can compute U, then you can compute this error exactly. But the question is, can we estimate this error without actually solving for U? Right? So the answer is, so before I talk about certain estimates which are possible, for this sort of error, let me define some notations. So given U0, some approximation of a forward solution U will define error as E0. So U minus U0 is E0. Related to that problem, and I'm not going to talk about that, is the adjoint problem in both the adjoint problem of our original high fidelity problem and also adjoint problem for surrogate problem. So let's say P is an adjoint solution and P0 is an adjoint solution of a surrogate problem. Then we can define another error in adjoint, which is called epsilon 0. I'll denote by residual of original problem, high fidelity problem by R. So it's linear form minus semi-linear form. And then residual of an adjoint problem of original problem is R bar. It takes this form. So you don't have to go into detail for now. Now, given these notations, one of the estimates of this goal-oriented error is basically, so U0 is a solution of a surrogate problem, so it's easier to evaluate. So assume that we have U0 already. So one of the estimate takes this form. So that estimate is basically residual, evaluating residual at this given approximate solution U0 and given approximate adjoint solution P0. And then you have another residual which is evaluated at E0 and epsilon 0, which is error in adjoint. Okay, and you assuming that an error residual is linear in the last argument, so you can sum P0 and epsilon 0 to basically have this reduced expression, which is evaluating residual at this given approximate solution U0 and the adjoint solution of our original problem P. Okay, so what is the problem with this estimate? Well, the issue is that this estimate still depends on original solution U and the adjoint solution P. Why? Because to compute adjoint solution, you have to know U. This solution, this P, depends on the exact solution U. Right? So now the question is there a way to approximate the error E0 and epsilon 0? So if we have some estimate of this error epsilon 0, we can substitute that estimate here, and then the resulting expression will not depend on this pair of original solution, right? So this brings us to this another question, and in this talk, it looks like I am asking like a lot of questions, but this is the question that will ultimately give us what we really need. So is it possible to approximate the errors E0 and epsilon 0? So the question is yes, and I'm not going into detail, but the calculations are very elementary, and this really goes back to sort of this classical work by Dr. Oden and also some other folks in that time. And the answer is here. So given any approximation U0 and P0 of U and P, and with this notation, E0 is the error in the forward solution, epsilon 0 is the error in adjoint solution. So we can estimate those error E0 and epsilon 0 by these estimates E0 hat and epsilon 0 hat by solving these uncoupled linear variational problems. And B prime is a derivative of semi-linear form with respect to the U. And then you have residual of adjoint sitting here, and you have residual of original problem sitting here. I'm sure many of you are familiar with this expression. And the key things to note about here is that these approximate problems for error epsilon E0 hat and epsilon 0 hat are linear and decoupled. So you're only solving linear problem to get these estimates of error, okay? And once you have those estimates, you can come back to this sort of one of these goal-oriented estimates, and you can substitute epsilon 0 hat here to build a cheap estimate of this goal-oriented error. Okay. Now, so that having said that, in this work that published last year, what we noticed, and it's not a big thing, but what we really noticed is this. So given U0, any estimate of a solution U, we have a true error, E0, which is U minus U0. And we can estimate that true error by E0 hat by solving this linear variational problem. And then we can add this estimate E0 hat to the estimate U0 to get a new prediction of U, okay? And once we have new prediction of U, we can compute the goal-oriented error easily. So you have Q of U minus Q of U0, which can be approximately equal to Q of U0 plus E0 hat. So here I have replaced U with a new prediction of U and subtracting by Q of U0. So this is another estimate that you can cheaply compute by solving this linear variational problem for the error estimate of error E0 hat, okay? So this is basically what will lead to, this is basically, you can see here that if neural network gives me an estimate of a solution by neural operator, then I can compute the error like that here, E0 hat, and add it to the whatever estimate neural network has given me to build another prediction of U, and then use that to do downstream calculations. But before I really bring this machinery to neural network, let me talk a little bit more about my work that appeared in JCP. So here now we want to use that estimate to solve this problem of calibrating high fidelity model. So consider this scenario. So given a high fidelity model involving unknown or poorly specified parameter theta, and also let's say we have some low fidelity model with its own parameter theta 0, which we'll assume that we know with acceptable accuracy. And also let's say we have one of these computable goal-oriented a posterior estimates that do not require solving the high fidelity problem fully. And then the question is, can we estimate the distribution of parameters theta in high fidelity model? That is, calibrate the high fidelity model with these three scenarios, okay? And we can, so let me now talk about Bayesian inversion formula to calibrate the high fidelity model using those estimates. So assume that the low fidelity model provides a way to observe the ground truth. So let's say G is a ground truth, and Q of quantity of interest computed using the low fidelity solution U0, and is a way to observe ground truth with some noise E epsilon here. And then also assume that high fidelity model is imperfect. So high fidelity model also can give you the estimate of ground truth, but it comes with a model inadequacy comma here. We can combine these two expressions to basically get this formula. So ground truth, or the measurement of ground truth Y minus quantity of interest on a high fidelity solution U is equal to noise plus model inadequacy. We sum them and assume that total noise is epsilon bar, right? And then we apply Bayesian scheme. So assuming that this total noise is Gaussian, very standard assumption, we basically get this likelihood function, Gaussian likelihood function, where at the heart of this likelihood function is the goal-oriented error here. And this is where I'm going to use the estimates. And then we can apply Bayes rule to sort of relate likelihood and prior to the posterior, right? And then here at the heart of this likelihood is the goal-oriented error, and where I'm going to basically use one of these estimates of a goal-oriented error, which basically entails solving for the estimate of error E0 hat and epsilon 0 hat, okay? So let me now briefly talk about the application, and then I'll come to the neural network. So as an application, we look at this very simple quasi-linear elliptic boundary value problem. So here you have a nonlinear diffusion term here. So kappa is some real number, and then you have 1 plus u square, grad u dot grad v, and then we also have this linear term alpha u v, and f is some prescribed function. So b here is basically linear in theta, but it's nonlinear in solution u. And then as a surrogate, we consider linear elliptic boundary value problem as a surrogate. So we basically discard the nonlinearity here, discard this additional term here to get this surrogate problem. So we have kappa 0 grad u0 dot grad v0. This gives you another linear form b0. And then we, as a quantity of interest, we consider average of solution u over the domain, or not average, but integral of u. And that is our quantity of interest functional. Very simple domain, square domain with Dirichlet boundary condition, and very simple reasonable function spaces here. Now, so I basically solve this. Basically, I use MCMC sampling to sample from this posterior, right? And here I have two ways to go about it. So one is compute this error exactly. That basically means I have to solve the original problem exactly and then compute this error. That's one approach. I'll call it exact, so-called exact. I put it in quotation because that is not really exact. There is numerical error here. And the other approach is to use, I'm going to use this estimate of quantity of interest error, right? So there are two approaches to come up with posterior samples. So I'm comparing them here. So the green one is the so-called exact posterior density I get. by basically solving the original problem and computing the original goal-oriented error accurately. And then the orange one is something where I use the estimate of a goal-oriented error, right? And this is posterior distribution. And we can also look at numbers. So here, it's a mean of those unknown parameters in high fidelity model, kappa and alpha, between these two methods. So one is approximation of quantity of interest error. The other is exactly computing that, and they are very much close to each other. So this is something we tried in our JCP paper, and this is what led to the approach now I'm going to describe with regard to neural operators. So let me come back again to the topic of neural operators. So we have this definition of neural operator, and basically we are looking at a neural operator that approximates the solution operator of some PDE in this form. And now let me talk about corrector operator. So given U0, some approximation of solution U, we looked at this problem previously. So we can compute estimate of true error E0. We call the estimate by E0 hat by solving this variational problem. And then we can use that estimate, add it to the given prediction to get another prediction of U. And I'm going to denote this approach by a corrector operator. So FC is a corrector operator that takes in as a model parameter theta as input, and it also takes in the prediction of a solution U0 as input, okay? And gives you another prediction of U, and then we are going to use that with neural operator. This is a schematics of the approach I have in mind. So theta is an input. You feed it to neural operator, it gives you some prediction U0 for that theta. You feed that theta to the corrector operator, you feed that prediction that you got from neural operator to this corrector operator, and you get another solution, prediction of U, which is corrected solution in this manner, okay? Now, why this, well, there are two things to note about this corrector operator. One is that it's nothing but a Newton step, if you really think about in that way. And why it is useful is because of this theorem. And there are more advanced theorem that basically based on Newton-Kantorovich theorem, which I'm not citing here. But this is a simple theorem that you can very easily prove. It just involves a little bit of calculus. And this is, let me go through the theorem and then you'll see why this corrector operator is nice and why we are interested in that. So assuming that, so theta and U, let's say those are Banach spaces, and R is a residual that depends on the parameter space theta and the solution space U. And then for given theta, let's say U is a solution of the residual problem. And then let's say U0 is any arbitrary approximation of solution U. And with that, also let's assume that R has certain nice properties. For example, grad U of a derivative of R in a Gattuso sense is invertible. And also second derivative of R again in Gattuso sense is bounded. Then you can show that the error in the corrected solution EC is below some constant times the square of the error in the original problem. So E0 is the error of U minus U0. So U0 is some prediction of a solution. EC is the error after, basically EC is the error given by U minus UC, where UC is a corrected solution. So here what it basically says is that if this constant is bounded, then the new error is less than or equal to C times the square of this prediction, original prediction error, okay? And this is why this thing is of interest to us. If E0 is within some bound, is already small, then the new error new error will have almost double, will have like the new error will be below, it will have like a quadratic order of reduction in error, right? So because of this relation. So this is why it is interesting to us, and we also numerically that this is actually true with the kind of problems we are solving. So since neural net operators are fairly advanced technique at this point, you can assume that the prediction is fairly good. Therefore E0 is already small enough, and then with this sort of corrector approach, you reduce the error by double order of magnitude. So let me now show you by this demo problem. So we consider a square domain. It's a simple nonlinear diffusion equation. So here you have this linear diffusivity here, and then you have this nonlinearity sitting here, U cube. And then f is some prescribed function over the domain. We have Dirichlet boundary condition on this part of the boundary, and we have zero flux on the remaining part. Okay, and then let me talk about what kind of neural operator I have. So I consider PCNA type neural operators. I'm fairly new to this topic, so I started with a very simple, neural operator. And the key concept about this is that we use SVD to use SVD to reduce the dimension from finite element approximation of function spaces for input and output. From that, we reduce the dimension using SVD, and then we have a neural operator, neural networks as a map between those reduced dimensions. So here, input goes to the centering layer. So you first center the data, then you reduce the dimension using SVD projection. Then you basically match the dimension to the output dimension, and then we have 5 ResNet layers here at this core, and then we get a output layer which we project it back to the finite element dimension. Okay, and as I said, we use SVD to project into reduced dimensions, and I consider combinations of input output reduced dimensions. So 50 is the input dimension, 25 is the output dimension. And I consider different input-output combination of those dimensions. And I also consider different numbers of training data. So, in these numbers. So let me now give you a sample of errors.
Can I ask a question? Can I ask?
Yes,
a question?
yes.
If you go back to that architecture, why is that an operator?
Yeah, it's an operator because it takes a finite element function as an input and gives you a finite element solution as output.
I mean, the operator don't know about finite elements.
Yes, it doesn't know, but operator is defined as a mapping between function space to function space, in which case this is.
So any neural network is an operator, is a neural operator.
As long as you see that in that way, if neural network maps from a coefficient space to a coefficient space of finite element, then it can be defined as a neural net operator. Yes.
So a CNN is an operator then.
I'm sorry, what?
CNN is an operator.
I mean, I'm saying, do you disagree with that definition that I just said, or I don't understand the question? Like what I said is wrong in some sense, or?
There are papers that by Sid Mishra that define exactly what is the representation for a network to be called neural operator, and this one will not pass the test. So you can.
Okay. So maybe if you can, maybe after this talk, if you can make some comments on that, it will be.
It's called the REMI.
Yeah.
It's called REMI representation. So.
Okay.
So,
I mean, I'm Dr. Karnadikis. This is like, I'm just jumping into this area. So maybe, I
email.
Looking forward to learn more. Yeah.
I told them. I told Karen and so on. They don't. Not every. Not every animal out there is a beast, and not every neural network is an operator.
Okay.
But it's fine. It's nothing to distract from your talk.
Okay, no. If you have some references on that, I would like to learn more. Yes. So I'm open to, criticism. That's fine. Okay, so let's come back to, if you can believe that is a neural operator. Okay.
Excuse me, I have a question in the previous slide.
Okay.
Yeah, this is Kamal from Brown. So the output layer is not a function of the coordinate. So it's only predicting the output as the point where training is there.
No. So output is actually a coefficient of a finite element representation of a function. Okay. So once you have those coefficients, you can reconstruct the finite element function, and then that's a function. So it's not a spatial point-wise evaluation. It's like a coefficient space of a finite element to a coefficient space of output finite element, and that's that mapping. So it's not a spatial point-wise evolution here.
Okay, so it's not continuous type of.
No. So let me clarify. So if you have a function, let's say H1 function, you can do a finite element approximation of that. Let's say linear Lagrange interpolation, right?
Yeah.
So, and then in that representation, you have coefficients that multiplies to this interpolation function. So this coefficient vector is an input to this neural network. And then output is also a coefficient vector of some function, some finite element function space. So it's not like a spatial evolution as you do in DeepNet. Okay, it's slightly different from that. Okay, so let me now show you how this corrector operator helps you in reducing the error, right? So with that approach I just talked about, we randomly sample the input parameter diffusivity in this case. So exponential of this function is diffusivity, to be correct here. So we randomly sample M here, and then we can solve the original problem. It's simple for a problem. So this is a true solution. And then with the neural network trained with one of the highest number of training data I had, and with a good amount of less large enough input and output reduced dimensions. So this is one of the best neural network I had. So on an average, it makes about 2% or above 2% error. But when you sort of use this prediction, feed it to a corrector operator and get a new prediction, the error you see is reduced by almost 2 orders. So here you have 2.4 percentage of error, and then in the corrector you have error as 0.05. Okay, and it's consistently seen for range of these random samples of parameter.
Sorry, are this?
So this is yeah.
Sorry, Prashant. Are this?
No, go ahead. Yeah. Feel free to yeah.
Are these percentage errors, or what is it? 2.4? Is it 2.4 over 100?
This is a percentage error. This is a normalized percentage error.
Okay, so it's 2% for 10% and so on, right?
Yes. Yeah.
So your error bound then it seems to apply, right? Because you take a 2%, 0.4% square, so that becomes 525. So you're almost there.
Almost there, yeah. With this problem, I don't.
Yeah. The first one, yeah.
And it sometimes it does good, sometimes it does bad. I have like statistics in the paper where I talk about maximum of this error for some 20 or 30 random samples, and also minimum and the mean. So on an average, it does like that. But sometimes because it's still a Newton step, so you are not guaranteed that you'll always have quadratic error reduction. So you sometimes see that. But on an average, for let's say you take large number of samples and compute the average of reduction in error, you see this quadratic error reduction. So which is nice, and it fits so nicely with the neural operator approach, because neural operator already takes you so close to the original solution. So that is like one of the restriction of a Newton step. If you're already close enough to the solution, then you really see quadratic error reduction, which neural operator does it for you. And then with this additional one linear problem solved, you gain 2 orders of accuracy. So, and let me now talk about more substantial problems. This is just a demo thing, just to show you some numbers. But let me solve a topology optimization problem with this approach. So we have this same nonlinear diffusion equation. So diffusivity is linear, nonlinearity is here, forcing function is 0, and I considered these 2 circular voids in the domain. And on the internal boundary of these voids, I fix temperature to 0. And outer boundary, all of this outer boundary has flux described equal to 0.1. Okay. Now the optimization problem is this. So we want to minimize the compliance of this problem. So compliance is basically heat flux times the temperature. So here you have heat flux as 0.1. This is a solution for a problem. And we want to minimize this quantity. We want to find M that minimizes this quantity. And also there is a volumetric constraint on the M, how much of M we can use. So neta is some given number. So on an average, optimized M should have this constraint. So these are optimizing problem. I'm not going to go into detail on how I solve that problem. I provide like complete details in the paper. And this is so I'll spend some time going through this slide. So basically this is a iterative simulation of iterations, optimization iterations. So here on the left top, I basically am plotting the numerical minimizer of that problem, right? And when I'm solving the original problem truly, so basically here, this sort of forward solution, I basically solve that exactly up to numerical error. And this is that plot. So it's a kind of a true minimizer in some sense. And then I considered I have like 20 different neural operators based on different combination of input, output, reduced dimension, and also different combination of training data. So out of those, I pick like 3 neural operators as a demonstration. So here is a neural operator 1, here is a neural operator 2, here is a neural operator 3. And what I do here, sorry, I'm going back again. So goal is to really, one option is to solve this operator exactly by solving this problem. Second option is to use neural operator here as an approximation. Third option is to sort of use neural operator plus the corrector scheme, right? So neural operator gives you a prediction, apply the corrector and put it here, right? So 3 approaches. So this is the first one where I'm showing exact minimizer. And then these 3 neural operators shows the results of that approach. And then when I add the corrector to the neural operator, I get this result. So neural operator 1 with corrector here, neural operator 3 with corrector, and then neural operator 2 with corrector. And you can see that, in general, neural operator leads to wrong minimizers, which are quite far away from the true minimizer. But when you add this corrector problem to support it, you get very close to the true minimizer. In fact, you can compute the errors in the minimizers. So these are again percentage error in the minimizers on the left hand side. On the right hand side, it's a percentage error in the forward solution at the minimizers. Okay, so on an average, neural operators, they lead to error as high as above 65% here, and as high as 80% for all 20 neural operators I considered. And when you add correction, the error is really below 6% here, as you can see. So these are summary statistics. So error with neural operator in minimizer is as high as 80%. And when you add corrector, you reduce the error to 6%. So I think with that, I am going to conclude this presentation. So let me make some comments here. So approximations based on neural operators, they do have potential to accelerate the computation. However, they suffer from unpredictable accuracy. An optimization problem that I discussed that shows the limitation of neural operators when a priori informative training data cannot be generated, which is kind of true for optimization or Bayesian inverse problem. And then proposed corrector method is based on solving a linear variation problem, thus has a reduced computational cost. And future work will explore the application of this work to critical problems and further reduction of the computational cost by developing approximation of a corrector problem itself. Okay. So with that, I will conclude this presentation and thank you. And I'm open to any questions. Feel free to, thank you.
Yeah, hi, this is Anirudh from Brown. I have a question. So the error that you are showing, is it for the train or the test cases?
No. So this is, I trained the neural network, like all 20 of them, to minimize, I trained it. And then I deploy neural network in this optimization problem right here. So F is a forward solution operator, and instead of solution operator, I use neural network operator here. It's a trained neural network that I use here, right? And then, so 3 approaches. One is that you can solve the original problem this here and use this U here. You can get a prediction of U from a neural network, trained neural network, use it here. Or you can get a prediction of U from a corrector approach and put it here, right? So 3 approaches, and here I'm comparing the error in the approach where I use neural network prediction as compared to the exact minimizer, and it makes as high as 80% error. And in the second here in the orange curve, I compare the error in the minimizer when I use the neural network plus the corrector approach, and compare with the true minimizer, right? So that is that. So it's an error in the minimizers. So I already trained the neural network. I did not talk about that because I thought, if people are already very much expert in that area. So this is a final result with the trained neural network. I hope that clarifies it.
Yep. Okay. Thank you.
Prashant, did you try to? I think this work is interesting, and I think it will be useful to try at least 2 neural operators. What you have is probably the Texas Austin neural operator, which doesn't qualify as an operator, but But let's say if you take a DPONet and FNO and you try to do the same problem and see if your correction is valid and compare. There's lots of operators now. We have the Laplace neural operator. There's all these transformers, Ditto, Vito that we developed. And so they give you good results. They don't give you errors 80% and so on. You can always make the error bigger, but I'm talking about true neural operators, and see that actually your corrector is useful across this plurality of different operators, not just something that happens to be developed at a very small part of the world.
No, you are right, Professor. And this is something I have in mind because, it has to be fair comparison to make this kind of comment. But this is a paper I really wanted to write very quickly. And then, follow-up paper is going to be, fair comparison with different neural operators. But I do think the result I see will stand valid. The reason is that it's kind of a cheating problem, this topology optimization problem. It's cheating because, you cannot train a neural network with the optimal solution already. You don't know that a priori. So no matter what neural operator you use, you're in a iterative scheme for solving this topology optimization problem. You're going to hit those iterative parameters that will be far away from the input space of a neural network, whatever neural network you use, and then therefore the error will still be there because it's of the error here is
not necessarily. Because we did a flow optimizing a shape optimization for an airfoil, and lift and drag, and so you can be, if you bring your bounds and the distribution that you're looking at large enough, you're actually going to be inside the distribution, in which case the errors are relatively small. If you hit parameters outside the distribution, they would become large, like 20%, 30%, something like that. That's sort of more typical.
I mean, yes. So I think I would be interested in learning more about that because I thought that it's more of a limitation of interpolation in this case, but
no, not at all. No, the interpolation you can get. That's why the approximation property. That's why I said, for example, DPONet is based on the theorem approximation, universal approximation theorem. So it guarantees that the approximation will be small. So that's not the issue. Yeah. I don't know if others.
Yeah, I think I'm definitely into comparing this approach. With different neural operators. I think that will be interesting to see. That will be fair.
Yeah, it'll be useful. Yeah. Alina, did you have a question?
Yes, I have some questions. Hi, I'm here at Brown, so I would just like to ask you. So would you say what you are doing is basically just obtaining initial guess for your standard finite element solver?
Yes, that's what I'm doing. Nothing fancy here. It's basically Newton step.
Yeah, so basically then you can get the error as down as possible or to machine precision if you would do more Newton steps, right?
Yes. If you can continue to go into this in this iteration, you could further reduce the error. But it's
okay, so then my next question is, do you have comparison where you basically just take random initial guess and you see what solution you get from your 1 Newton step? Does it even pay off to initialize?
No, so so it won't work, right? Because there is no magic here. If you take a random solution which is like far away from the fixed point of a problem, then you could make a large error with the Newton step. I mean, so it works really nicely with the neural operator because it gives you a prediction which is already close enough to the solution. So 1 Newton step gives you quadratic error reduction, but you randomly give it any guess. It could work, it may not work. And
yeah, exactly. So, I mean, this depends how good is your initial step, right?
Exactly. And therefore, it works nicely with neural operators because neural operators already are good enough.
Yeah, but I think you can still compare in a way to somehow quantify.
Numerically, I compared, but what's the point? Okay. Because you know that any random guess will not give you good solution.
I don't know, depends on PDE, I would say, but so then I have also one more question regarding type of PDEs which you consider. So I mean, this is related to the fact that Newton method is not convergent if your initial guess is not in the local neighborhood of the solution. So would you consider any, I don't know, non-convex PDEs and so on?
Actually,
like, how would you address this? Do you have some line search or trust region globalization strategies, or?
No, so yes, those things will come up, but basically what I'm trying right now is to solve this topology optimization, and that was my original motivation to solve this problem. Is basically to solve topology optimization of functional soft materials. So this is basically nonlinear hyperelastic material models, and then the Young's modulus and Poisson ratio, they all depend also on the volume fraction of whatever inclusion you put in. Let's say it's a functional magnetic material, so it's extremely nonlinear problem. And I really want to deploy this sort of approach to that problem, because there, even the Newton steps, you have to make like almost 10, 20 Newton steps to sort of converge to a solution every time step. So I really wish to apply to that problem, but yeah, it's something I'm doing, but I don't have results right now. Yes.
Yeah, I was just curious if that's the direction you plan to take.
Yeah. I mean, I really want to solve that topology optimization for the soft materials, because I think that's where these things are toy problems. So it's nice for a paper, but the real problem is there.
Yeah.
Yes.
Okay. Thanks.
Yeah.
Hi. My name is Vivek, and I'm a PhD student working with Professor George Karniadakis. So I have a question for you. So how well this approach generalizes across different boundary conditions? So for example, for a different G of X, how well does it work?
It works because, there is a paper here. So let me also put that point here. So this is a collaborative paper with colleagues here, Liang Hakao, Tom O'Reilly Roseberry, and also Dr. Oden and Omar Ghatas. So here in this paper is basically the same approach, but here in the follow-up paper I give it a fancy name, corrector operator, but basically we deployed the same approach in this paper. And there we solve the Bayesian inverse in infinite dimension, Bayesian inverse problem of a hyperelastic material model. So you have a hyperelastic deformation of a square domain. You have some kind of prescribed traction on one side is fixed, and then what you're trying to do is you have some data, and then you are trying to infer the Young's modulus field in that domain. Now that problem is extremely challenging, because you're dealing with large deformation model, so it's a nonlinear problem, highly nonlinear problem, and it works. With this approach, we do solve that Bayesian inverse problem, and it works very nicely with this approach. So I'm hoping that the problem that I just described to Alina, with this topology optimization of soft materials, I hope that this will go through with that problem also, because we already demonstrated that it works for a hyperelastic material model. So.
Okay, thank you.
Yeah, thanks.
Any other questions? All right. Thank you, Prashant, for your presentation. Thank you for the discussion. George, you want to comment something?
No, just I want to say to Prashant to say hello to Tinsley Oden. I'm the good friends, and the first
will do.
The first awardee of his Tinsley Oden medal. I have it right here.
Oh, nice. Okay, let me take the photo and show it to Dr. Oden.
This is I was the inaugural recipient of the Oden medal.
Okay, I'm taking a photo. 1 second.
Okay,
I'll
we're uploading this video to YouTube, so you can always double check on YouTube on our channel.
Oh, okay, that's good. So you're going to upload this video to YouTube, really?
Yeah, we have a YouTube channel. For
otherwise I would have prepared better. So.
No, you did well, Prashant. It's fine. Okay, good luck.
But thank you so much, Professor, for this opportunity. I enjoyed talking to you, and hopefully in the offline we'll be in touch. Yeah.
Okay, great.
Okay. Bye-bye. Yeah. Bye-bye all. Thank you.
Yeah. So goodbye, everyone. See you next week.